Welcome. In this video, we're going to expand our knowledge about the principle of mathematical induction to something that is normally called strong induction. So the principle of strong induction is where we'll start. So again, we're going to start with some statement, some proposition about all of the integers, and we're going to try to show that that statement is true with a base case and with an inductive step, just like the regular principle of induction. Strong induction is going to look slightly different, especially in the inductive step. So in the base case, again, we need to start with some base case. We might need to do this for other values as well, depending on how our chain of implications goes in the particular problem we're doing. So as we see more examples, we'll see when we might have to show more than one base case. We'll always have to show one base case no matter what. Now for the inductive step, let's say we're viewing the problem as a line of dominoes. And in regular induction, you've got one domino knocking over the next domino to create this chain reaction effect of true statements. Well, let's say maybe the 100th domino was really heavy and the 99th domino didn't knock over the 100th domino. But if you considered all the weight of the previous dominoes falling over, that would provide enough weight to knock over the 100th domino. And the same goes for every other domino. So we could look further back. Instead of just looking at P sub n, why not also use, if you need, any smaller statement that you already know is true? Let's unwind this a little bit in a picture. So let's say you have some statement, it's about the number 1, just as a nice starting point, and we show that that's true in a base case. And then we successfully show that 1 gives us 2. So our chain is starting. And then we want to know about the statement, is it true for 3? So you could use the knowledge from 2 to help you to get to 3, but maybe that's not the most convenient way for some examples. Maybe it also helps to look back at 1 to help you get 3. And in addition, you can use any information you learned about when you're talking about the statement with 2. And then similarly, once we get to 4, why not look all the way back to 1 again? And maybe 1 helps us get information about 4. And maybe 2 also helps us get information about 4. And then 3 in addition. So this chain of thought process goes on and on and on. And you can also use this different type of chain of implications to show that statements are true about the integers. Now, there's not a particular big advantage over strong induction or regular induction, other than in some examples it's more convenient to look at previous steps other than just the very previous one. So either strong induction or regular induction, you'll get a bunch of statements and you'll be able to show they're all true by the methods. One might be more convenient than others for different examples. So let's look at some examples. So here's a classic example that you'll find in lots of textbooks where we're introducing strong induction about postage. So when you take an envelope and you start sticking stamps on that envelope, each stamp can be worth a certain amount and it'll add up to the grand total amount of money you have towards your postage that you're sending away. So just suppose that you only had the ability to stick on 4-cent stamps and 5-cent stamps at a time. This problem says that we can make all possible postage out of 4s and 5s if we're assuming that we're only worried about values bigger than or equal to 12. Okay, so like 12, for example, you could make with 3 4s. That would total a postage of 12. And then what about for 13? What about for 14, 15, and so on and so on and so on? So this is a situation where strong induction really shines. So we're going to write down our base case to begin with. So base case, what we want is to start at n equal to 12. And we're going to show that p sub 12 is true. And we might have to do this for other values also. So remember that comment from above. So I'm just going to leave it at p sub 12 for now, and maybe we'll have to look at other examples further along. So for 12, as we were saying, we can take 3 times 4, so 3 4-cent stamps, and let's write 0 5-cent stamps. That will give us a grand total of 12. So the base case might not be done at this point, but it certainly has this one case where we absolutely need to write that one down. So let's take a look at the inductive step next. Let's just leave a little bit of space if we need to complete more in our base case. To figure out if we need to complete more in our base case, we really need to do the inductive step first. We need to decide how we're going to plan out doing our inductive step. So what to write down or what to try to show here takes a little bit of practice before we get a feel for what's going on in particular problems. In this particular problem, you're working with the number 4 and the number 5, and you're trying to build integers with the 4s and 5s, as we did above. How many 4s? 3 4s, and how many 5s to build integers. So it might be a good idea to look 4 steps back, or maybe 5 steps back. 4 is a smaller number. Let's just pick 4. So how about we try to show that p sub n plus 4 is true. And for this problem, to try to show that p sub n plus 4 is true, we're going to allow ourselves to look at any previous n value all the way down to n equal to 12. Okay, so again, I'll leave myself a little bit of space, and I'll try to think about how could I write the number n plus 4 in terms of 4s and 5s. So the 4 is already a 4, so we don't really have to do anything with that. But the n value, that's what I'm kind of interested in. N, how could I write that in terms of 4s and 5s? Well, we just said that we could assume that p sub n is true by using this kind of shiny new method of strong induction that we've just learned about. So p sub n would tell us that n can be written as 4 times some number, let's say x is an integer in this case, plus 5 times some integer, let's say y. So our red bracket replacement by p sub n works like this, and then we have a plus 4 to carry along with us. And let's just clarify that x and y in this case are integers. Just as a side comment here, I wrote x for, now usually in algebra when you're writing down expressions with variables, usually you write down like 4x plus 5y. The reason why I chose to write it the opposite way here was because I was really counting the number of 4s. I was saying, how many 4s do I have? I have x 4s. And usually when we're reading regular algebra statements, we'd say we have 4 x's. But here I wanted to emphasize that the thing that we were counting was 4, and the thing that we were counting was 5. Okay, so back to our problem. We're actually very close to finishing this off. We just need to rewrite this. So we're counting all the 4s together. So we have x plus 1, 4s, plus y, 5s. And that really completes our inductive step, because we've taken the number n plus 4, and it's equal to this, which is also equal to this, and the final part has just a collection of 4-cent stamps. How many? X plus 1, 4-cent stamps, plus a collection of 5-cent stamps. How many 5-cent stamps? We have y 5-cent stamps. So what we ended up doing in our inductive step is we used p sub n to conclude that p sub n plus 4 was also true. So we showed that p sub n implies p sub n plus 4. So I didn't even really know what I was going to use to help me get to pn plus 4 to begin with, so I kind of left a little bit of space right there so we could go back to it. Okay, so the inductive step is complete. I'll give that a red check mark. We've completed that part of it. We just need to think further about the base case. Let's try to think about the chain reaction that's occurring here. We've shown that our statement is true for 12. And then in the inductive step, we were able to show that it's true for 4 more. So like 16, for example. And then once we know it's true for 16, we could also get that the statement is true for 20. But that's not quite what the problem asked for. It said everything bigger than 12, not just up by 4, multiples of 4 starting at 12. So if we return to our base case and we show that our base case also works for 13, then that would give us 17. Once we get 17, then we would get 21. So that's a step in the right direction. And furthermore, if we showed a base case for 14, then that would give us 18. 18 would give us 22. And then finally, if we showed an explicit base case for 15, that would give us 19, and then 23. And notice, now we don't have any gaps. If we just keep going along in this process, so ... continue on and on and on, we would create a sequence that doesn't miss any of the numbers bigger than or equal to 12. If we just kind of count across here, we have 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, so on and so on and so on. We didn't miss any. So that's just a cloud that's off to the side of our thought process. We don't really need that formally in our process of strong induction, but we do need to return to the base case and show some explicit cases. We need to make sure that we can calculate out 13, 14, and 15 to add in. So 2 times 4 plus 1, 5 would give us 13. And 1, 4 plus 2 5s would give us 14. And then finally, no 4s and 3 5s give us the last part of the base case, giving us 15. So to return to what we were trying to do, we wanted to show that p sub 12, p sub 13, p sub 14, and p sub 15 are true. And we successfully did that below, and that completes the induction, and it gives us a solid proof that says we can make all the postage with 4s and 5s for every integer bigger than or equal to 12. All right, so next we have another strong induction example to work on. We're going to try to do the following and show that every positive integer can be written as a sum of distinct or different powers of 2. So we're going to go through the same process over again. P sub n will be our statement, so let's write that down. And the problem says every positive integer, so our P sub n that we're trying to prove here is for n's that are bigger than or equal to 1. Okay, so let's start out with a base case. In our base case, the number 1 can be written as 2 to the power 0. So that's a cheap and easy way to get through our base case, at least thus far. So we now know that P sub 1 is true. So I'll leave a little bit of space. I'll go down to my inductive step and I'll try to think about how we're going to make a conclusion here. So this time around, I have a problem that's dealing with powers of 2. So that makes me think it's natural to look back with powers of 2 in mind. So powers of 2, double as they go forward, or as they go backwards, we would half them. Like, 2 to the power 3, and half of that would be 2 to the power 2. So how about we look back half as much? We're trying to get p sub 2n, and maybe p sub n will help us get that one. So I'm going to write 2n down on my page, and my goal is to try to write out the number 2n as a bunch of different powers of 2. Okay, so n right away is helped along by p sub n. P sub n tells us that n can be rewritten as a bunch of different powers of 2. Okay, great. Let's just make up a bunch of powers of 2. Let's say 2 to the power I to 2 to the power j. And it's important to note that these powers are all different. So the I and the j are different, and every single power along the way is different. Let's notate that. So we have a bunch of different powers. And if we multiplied the 2 into these brackets, so we expand it out, so we have a whole bunch of different terms, each of those terms will be a power of 2. It'll be something like 2 to the power I plus 1, and then plus dot 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 all the way along to our last one, 2 to the power j plus 1. And the i's and the j's, all these powers of 2 are different, and we just bump them all up by one value. So we still get distinct powers. So again, each of these powers that are in this list of powers of 2 are different. Okay, so that's good. We've got 2n written as different powers of 2. Now, that doesn't quite give us everything we want. There's a problem here. We're supposed to do this for every positive integer, every integer bigger than or equal to 1, and we've just picked this arbitrary number 2 times n. Now, unfortunately, 2 times n will only represent even integers. We also have to consider the odd integers as well. So an odd integer would look like 2n plus 1. And from what we've written above, 2n plus 1 would be 1 more than the previous line that we just wrote down. So the 2 to the power I plus 1 plus dot 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 dot, the 2 to the power j plus 1 plus a 1 at the very end. And once again, these are all distinct powers. They were distinct powers above, and now they're distinct powers below. Okay, so what we have to do is make sure that the number that we've written out over here is a bunch of different powers of 2. So the only problematic term is this one right here, 1. But luckily, 1 can be written as 2 to the power 0. So let's do that. So we would have 2 to the power I plus 1 plus dot 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 2 to the power j plus 1 plus a 2 to the power 0. And then finally, we just want to verify that these are indeed all different powers. And they are, because I plus 1 and j plus 1 and everything in between all got bumped up by 1. So none of those powers are 0. And then there is a 2 to the power 0, but it doesn't repeat any of the previous ones. So indeed, all of those powers that we just wrote down are different. So we're now quite happy with our inductive step. We've shown that p sub 2n is true, and we've shown that p sub 2n plus 1 is also true. So what did we need to get us there? We needed p sub n to tell us both of those things. I'm just going to put brackets around those two, because this time we kind of hit the two birds with one stone. P sub n gave us both the even integers and the odd integers. And we should always quantify this. We should say, well, which n values did we show this for? So I'm going to squeeze in that we've done this for n values bigger than or equal to 1. And then finally, we'll just return back to our base case, and we'll think about, well, is there anything more that we need to show there? Is there any more base cases that we need to write down? Well, we've got 1, and then when we plug 1 into our n value below, it gives us 2, and it gives us 3. So let's write down that. 1 gave us 2 and 3. And then once we have 2, 2 gives us 2 times as much, which is 4, and 5. And then once we have 3, it gives us 3 times 2, which is 6, plus 1, which is 7, and so on and so on and so on. Notice we're not missing any integers. 4 would give us 8 and 9, and so on and so on and so on. So the only base case that we need is the one that we showed. We showed that this works. For 1, piece of 1 is true, and it gives us the entire spectrum of all the other integers. So let's just erase that. And our base case gets the check mark. We're done there. The inductive step gets our check mark. Both are successful in showing exactly what we wanted to show. Thanks so much for watching the video, and we'll see you on the next one.